Well, hello again. Welcome to our journey into linear algebra, and we've been looking at applications of symmetric matrices, and the main application here was to look at these conics, these quadratic forms in 2 dimensions. And in the last example we saw that we could take these conics and write them using a symmetric matrix, and then when we calculated the eigenvalues, they turned out to be real, and the eigenvectors turned out to be orthogonal, and that property enabled us to orthogonally diagonalize the matrix A, which meant that we had if we put the eigenvectors normalized into a P matrix, then P inverse is P transpose. And that meant then we could make this change of variable, and that turned the conic into one where we could recognize exactly what it was. Now, the key properties that we used here were the fact that we've got a symmetric matrix. We needed the eigenvalues to be real, and the eigenvectors from different eigenvalues to be orthogonal. So they were the 2 main properties that we want to be true in order for this technique to work more generally. And so our next theorem confirms all of these things that we want. So if A is a real n by n matrix this time, then all the eigenvalues of A are real, and the eigenvectors of A corresponding to different, and that's important, different eigenvalues are orthogonal. If you have an eigenvalue which has geometric multiplicity more than 1, then you can just do a little bit of fancy footwork to cook up the eigenvectors to be orthogonal. But in general, if they're coming from different eigenvalues, then they're guaranteed orthogonal. And it's worthwhile having a look at a little quick proof of these basic things. So firstly, if we take lambda to be an eigenvalue of A, so AV is lambda V for some vector V, and V is not 0, we want to show that lambda is real. Now at this stage we don't know anything about the eigenvectors, and so I'm going to multiply both sides by the conjugate transpose of V. Now of course we'll see that the V's are real, so the conjugate doesn't do anything, but at this stage we'll multiply by the conjugate transpose to obtain this. If we take the conjugate of both sides and then transpose these, so take the conjugate of each of these and transpose, we end up with this expression. Now of course A is real, so when you take its, and it's symmetric, so each conjugate transpose equals itself, so it doesn't change. And if we now compare these two, then we can equate the 2 right hand sides to obtain this. And now of course V transpose V, we can take the lambdas out, and of course V conjugate transpose V is just this, which is our inner product, our normal dot product for complex vectors, which is just the sum of the squares of the components of the vector V. So, and this thing here is it's not 0, and so if we now compare these two, this quantity here is not 0, so that tells me I can divide both sides by this quantity. It's just a number now, and I get lambda equals lambda bar, so lambda is real. Now of course, since our eigenvectors are in the kernel of A minus lambda I, the eigenvectors of a real symmetric matrix are also real. The other thing we wanted was that to show that the eigenvectors from distinct eigenvalues are orthogonal. So if we take U and V to be eigenvectors of A corresponding to different eigenvalues lambda and mu, that is, I can write this down, AV is lambda V and AW is mu W, where lambda and mu are different. So if I take lambda, if I now dot product, say lambda V with W, then lambda V is just AV, so that's AV dotted with W. And now, remembering what our dot product means, it's the transpose of this multiplied by this, so you take the transpose backwards. So V transpose A transpose W. Now A is symmetric, so A transpose is equal to A. and AW is just mu W. So that means, tracing that back then, that says that mu V dot W is equal to V transpose, well, sorry, by exactly similar calculation, just replacing the lambda with mu, we get mu times V dot W is V transpose AW, exactly the same calculation. And if we compare these two, then we see that lambda and mu are different, so V dot W has to be 0. That is, V is perpendicular to W. So that shows us that the eigenvectors from different eigenvalues are orthogonal. Now it can be shown by induction that if A is a real n by n symmetric matrix and A has n mutually orthogonal eigenvectors, and hence normalizing if necessary, we can put them as columns of P as we did in the earlier example, whack those orthonormal eigenbases into P, and P will be orthogonal, and that means that P transpose is P inverse, and that means that this matrix P orthogonally diagonalizes the matrix A. So that's a little bit of theory there that we needed, and we'll have a look at a couple of further examples of this. Then I just note here that if the eigenvalues with algebraic multiplicity greater than 1, then we may need to apply Gram-Schmidt to these independent eigenvectors from the same eigenvalue in order to obtain an orthonormal basis. Sometimes one can just do some creative cookery when cooking up the eigenvectors, in fact. So here's another example. We're going to identify and sketch the curve 8x squared plus 12xy plus 3y squared is equal to 48. And we want to find points, if any, on the curve that are furthest from and closest to the origin. So here's the worked solution for this. So here's our conic, and immediately we whack it into matrix form. So the x squared component goes here, the y squared coefficient goes here, and we share this equally between these two to give us a nice symmetric matrix. Now we know the eigenvalues are real, so we compute them usual way. We set the determinant of a minus lambda I to be 0, gives us a nice quadratic, and out come the two eigenvalues. Now, by the way, at this stage, because one is positive and one is negative, you can almost see what this curve is going to be. When we change variable, we're going to have a 12 capital X squared minus capital Y squared is equal to 48, and that's going to be a hyperbola. So if we were only interested in what is the shape, then at this stage we can predict that this is going to be a hyperbola. But we like to press on and get the principal axes and so on. So the eigenspace for 12, so we plug 12 in place of lambda up in this matrix. So we get minus 4, 6, 6 minus 9, and that's just the span of 3, 2. 3 4s are 12, minus 12. So minus 12 plus 12 is 0. The eigenspace for minus 1, we plug minus 1 back up into the matrix here. And again, we just I'd look at this one here and say, well, that's minus 12 plus 12 is 0. And so that's going to be the eigenvector. And notice that these are orthogonal, as the theorem guaranteed. If you dot product these, you get 0. So the length of each of the vectors is root 13. So I can take a 1 in 13 out the front and construct my P matrix. So here is my orthogonal P matrix. And I choose this here so that the determinant of this is 1. So just note here that the determinant of P is 1, so that it's a proper rotation matrix. Because obviously up here I could have put the minus down here, and that would have given me a determinant of minus 1. But I want the P to be a rotation matrix, so I choose it so the determinant is 1. Usual trick, we make a change of variable, we put xy as P capital XY, and then this matrix P orthogonally diagonalizes A into this diagonal matrix, and when we make the change of variable, plug it back in and expand out, we get this equation, which of course is a hyperbola. So I've drawn a little, not a very good picture, but I've drawn a rough sketch of the hyperbola here. We use our principal axis 3, 2, so across 3 up 2. So that's my new x-axis. And the other eigenvector was minus 2, 3. So minus 2, 3 was up here. So I draw this line through here. This is going to be my new y-axis. And with respect to those axes, we can draw the hyperbola. Now, it asks for the points closest to the origin, and there are no points furthest away from the origin, because you can go as far as away from the origin as you like on this. So I should really say there are no points furthest from the origin. No points furthest from the origin. Furthest from the origin. And the points closest to the origin are going to be these two here. Now these correspond to capital X is 2 and capital Y is 0. And we get two of them, plus or minus. Now we want to know what the points are back in terms of the little xy coordinates. So we use the fact that when we made our change of variable, we had little xy is p times capital XY. So I just take my p matrix, multiply it by this, and we end up with this here. So we get plus or minus 1 on root 13 times 6, 4. And that's giving me the coordinates of these points here, but with respect to the little x and the little y. Okay, so that's a fairly standard example of one of those. I'll do another one of these. Again, you might like to stop the recording and have a go and do it yourself. So this is 3x squared plus 4xy plus 6y squared is 7. I'd like to repeat the exercise again and stop the recording. And then you can come back so that you can compare your answer with mine. I've done the worked solution here to this. And once again, we start off with our conic. We write it down in terms of a symmetric matrix. We have to calculate the eigenvalues of this. If you've done this, you would have gotten 2 and 7, I hope, from that. Now the eigenspace for 7, whack 7 back up into the matrix. I get this one here. And if I look at that, say the bottom row, we get, I'll have 1 of those and 2 of those. So 2 minus 2 is 0. The eigenspace for 2, we put 2 back up into the original matrix, we get this. And again, I'm going to take I'll have minus 2 of those and 1 of those. So that's minus 2, 1, and that's in the kernel of this matrix. So whack these into a P matrix, but don't forget we have to normalize it. Make the usual change of variable, and then with respect to our capital X and capital Y axes, we have 7x squared plus 2y squared is 7, which is an ellipse. By the way, of course, it doesn't matter which order you put these in back here. Once I chose the order 7, 2, and then I've got to put the eigenvectors in the same position to give me 7, 2. If I wanted 2, 7, that's fine. You just have to do the eigenvectors in the opposite order in the P matrix. But again, I want the determinant of P to be 1 here, so it's a rotation. Just makes it easier when you go to draw the thing. So here's the picture of this. It's an ellipse this time. And again, the principal axes were 1, 2, so that's my new x-axis, and minus 2, 1, that's the new y-axis. You can see why I chose P to have determinant 1, so it's a proper rotation. Now the principal axes, as they're called, are the span of 1, 2, that's this x-axis, and the span of this one. These are called the principal axes. Now the points closest to the origin are going to be these two here, and I can get the little xy by just multiplying this by p, and I didn't get the points furthest from the origin, so I'll just do that now. Points furthest from the origin. Well, they're going to be these 2 points here on the, and they're going to be at x, y, is this time the x will be 0, and if we look back to here, this cuts the y-axis when x is 0, so that's plus or minus root 7 on 2. And so the little x and little y then are going to be, well, I've got to take the plus or minus root 7 on 2 multiplied by the p matrix. So I'm going to get a root 5 there, and this is now 0, 1, so this is minus 2, 1. And so they will be the 2 points furthest away from the origin on the ellipse. They correspond to these 2 points here. And that really is the all we're going to do for these conics in 2 dimensions. In the next recording, we're going to have a look at 3-dimensional conics. What happens when we take this up 1 dimension into 3-dimensional space and we have a look at 3-dimensional conics.